Howdy folks, I'm Keith Bowen and this is Hard Rock University. This lesson is on various separation techniques. Assuming you have a valuable mineral, in our case gold, in rock or in many cases placer and sand and gravels, you need to extract it into something you can sell. Okay? Now, there's a lot of different ways of doing that, and this is just kind of a broad overview for those who haven't heard of everything. So I'll start with kind of the oldest to the newest sort of thing, just because I got to categorize it somehow. Now the oldest technique is gravity concentration, starting with something like a gold pan. Now, these are gold pans that were sent to me by people when I asked for ideas on where those gold pans came from, and I got a heck of a response. People were sending me gold pans. Thank you very, very much. It was very useful. These are just the ones I haven't even used yet. You know, I got duplicates, etc. And I'm pretty stocked up on the 10-inch gold pans now. Thank you very much. I appreciate the interaction. It's really rewarding. But gravity concentrations rely on the difference in density between the gold and the other particles to separate it. Now, in order to get the gold to behave differently, it has to be physically separated from any other materials. If it's in sand and gravels, you would usually do this by screening, agitation, something like that. A trommel drum is a very efficient machine at doing that. It gets rid of the oversized screening. It also beats everything up and loosens the gold particles with clays, the whole 9 yards. It creates a whole bunch of separate particles and throws away the big stuff, all in one operation. Very efficient. So, in order to do a gravity separation, you have to get separate gold particles. If it's placer, it's usually done through just, you know, like in a dredge, you just suck it up and throw it over the sluice boxes. In a hard rock operation, you have to grind the rock up. It can vary enormously how much you have to grind it, and it's very much ore dependent, but you have to grind it sufficiently to achieve mineral liberation. And that means in some cases that can be more costly than other operations where you don't have to grind quite so much. But basic methodologies of the gold pan. It's very low tech, it's extremely portable, it's low cost, has a very low throughput, although depending upon your techniques, etc., you can recover some pretty fine gold with it, as you've seen in my videos. Then you have sluice boxes. Now, dredges usually use sluices. A lot of wash plants will use a sluice. Advantage of a sluice box: it's low tech, high throughput, low cost. If a sluice will do the extraction that you need, if it'll work on your material, it's really tough to beat. There's no moving parts, and it's extremely simple, runs for long periods of time between cleanups, etc. It's a very efficient system when it works well. When you start getting into finer gold, now you have more challenges to get it to separate out. They use jigs. A Denver jig has a pulsing action that keeps everything liquefied. I have the hydromatic jig that uses an oscillation and an upwelling to keep things liquefied. Basically, the gold settles through a fluidized bed. When you start getting even more tricky, you use separation tables. One reason you do this is because it operates on a very thin layer of material. You can get a quick separation into various layers. And the stratification can occur very rapidly and efficiently in a thin layer, where in a larger layer it's going to take more time, and it's going to have these boundaries between them that are kind of vague, where there's intermixed materials. So a thin layer has certain advantages. The negative is it really cuts your throughput down, and it generally will require a tightly controlled environment. Though you will usually, for example, bolt to a concrete slab to allow you to get specific vibrations and oscillations without, randomness being created there. They also tend to be fairly big and expensive. They're somewhat more complex. They require precise setup and tuning during operation to optimize your recoveries. But they can recover really fine gold and specifically give you a fairly clean concentrate. Now, the last gravity separation technique I'd like to discuss is something called dry washing. Dry washing is not as effective in general as wet processes, but it has the tremendous advantage in some areas of not requiring any water. The small Prospector scale dry washer is basically a high banker, but the sluice has been changed a bit. Here's a picture of one. You can see it looks a whole lot like a high banker. It has a classification trough on top. The big stuff goes off, the small stuff goes onto the sluice, goes down the sluice. The difference is, in this sluice, in order to get liquefaction, the bottom is porous and air is blown through it. Now, that liquefies things, but it also tends to lift the very fine gold. And because of this, they are not the best at recovering fine gold. There's some that are better than others, etc., but the general rule is, for really fine gold, you need a wet technique, not a dry washer. However, if the gold's coarse enough and the material is dry enough, if it's damp, you can't do a separation. The particles won't break apart. So it has to be very dry, and in those cases, sometimes it can work quite adequately. And in a circumstance where water is either unavailable or quite expensive, it may be your only viable option. So don't put it down. It's used a lot in the desert for prospecting, and they even have full-scale industrial size units for, again, those highly arid areas like some places in Africa, notably Australia. They do this quite a bit in Australia, and it's on a prospector scale in the southwestern United States. So dry washing can work quite effectively under some circumstances, but it's more of a niche technique because it really doesn't do well on damp material, and it doesn't do as well with real fine gold. So those are your basic methods of gravity separation that are in wide use. As a general rule, with a gravity separation, the more tightly classified by particle size, the better the separation. So there will almost certainly be some kind of screening operation involved here to maximize your recovery. The next thing to come down the pike was something called amalgamation. Gold is a hydrophobic material. It tends to repel water. Mercury is also a hydrophobic material, but liquid mercury wets gold. So if you run gold particles across a mercury surface, those that penetrate the surface tension immediately stick and stay. So if you take like a copper plate, clean it, coat it with mercury, and then run a slurry across it, you can recover gold. It's not the highest efficiency in the world, but it does work fairly well at fairly small particle sizes and works reasonably well with a slurry of crushed rock. The negatives are mercury is a cumulative toxin. It gets into your body, it stays in your body. You don't get rid of it very easily. and it can cause serious problems. It gets in the environment, it stays in the environment, it doesn't go away, it doesn't get degraded to something harmless. As a matter of fact, metallic mercury, when it's chemically altered, usually makes it more toxic. For this reason, it requires careful handling to be done relatively safely. Disposal of any wastes are expensive and complex, and permitting a mercury recovery operation, especially if you had, wastewater dumping or something, would be virtually impossible. It is not used in first world countries for commercial operations anywhere anymore that I'm aware of. It is sometimes used by individual prospectors quietly. I can't recommend it for legal advice. But it's often used in third world countries, and there's a push to create other techniques that will do as well or better to get these artisanal miners, as they call them, to stop using the mercury because of the substantial environmental impacts. It's not a minor thing when you have a bunch of people using a bunch of mercury and losing a bunch of it, which naturally happens. So amalgamation, while very common in the past, is very rare now, and they're doing the best they can to phase it out. Now, another method that uses the hydrophobic nature of gold and other minerals to recover it is something called froth flotation. Now, froth flotation has been used for a little over a century. It is by far the most common method of concentrating base metals from their raw ores. It works on the principle of you take a crushed slurry of rock, you expose it to certain chemicals, usually very low toxicity and in low concentrations in the slurry, that change the surface chemistry of those particles to make them hydrophobic, water repelling, or hydrophilic, water attractive, depending upon which mineral they are. If it's a mineral you want and you're making it hydrophobic, it would be called an attractant. If it is a mineral you don't want and you're making it hydrophilic, it's called a suppressant. There's a variety of them. The chemistry gets pretty complex, partly because it's extremely versatile. I mean, you can use it to separate potassium chloride from potassium, calcium chloride. I mean, it's just amazing what you can do with this. They use it in wastewater treatment. They use it to do a lot of different things because it's so versatile. But that versatility comes with a price, and that is the field is extremely complicated. But a lot of that complication is caused by the fact that it's just got so many different applications. It's like fasteners. There's a lot of different things you may want to fasten, so there's lots of different kinds of fasteners. If all you're dealing with is nuts and bolts, life gets a whole lot less complicated. In the case of gold and sulfide minerals, it's a lot less complicated. I really think there is a strong possibility that this could be used in micro to small scale operations quite effectively if we can somehow make the theory simple enough that the ordinary person working with the internet can operate an efficient system. Anyhow, the way the flotation works is you take the materials, you make what you want to recover hydrophobic, what you don't want hydrophilic, and then you bubble air through it. Just as gold can float on top of water, it will stick to the air bubbles as they come up through the slurry. Now, they do a number of things to make it work more efficiently. For example, they inject a whole lot of air and they use something, agitators, to mix this stuff so that the valuable particles will actually hit enough bubbles to stick to one of them. And this creates a froth. These bubbles float to the top, and they've just coated with these valuable minerals. And here's what it looks like when they do it. So it's very valuable. You can separate different minerals. You can separate galena from other sulfide minerals, sphalerite, by using different attractants and suppressants in sequence. So you get a lead concentrate here and a zinc concentrate there from the exact same ore in the same line. Again, extreme versatility and essentially fairly low cost. This works very well, especially on large scales. Low cost, low toxicity, extreme versatility, high recovery rates. It's very good. It's the complexity that makes it more difficult for a micro-scale mine. And I'd love to work with people to try and make that a lot simpler for micro-scale miners. In addition to that, there's another technology which I've read about. I don't know anyone who's done it, and the literature is just not specific enough. They call it cold gold agglomeration. What they do is they take granulated coal, which is kind of a porous carbon, and they mix it with oil and stick it into particles, and then they use these particles, they mix it with the slurry, and they agitate it, and the gold will stick to the oil and work its way into the particle. And it's kind of like how you would use carbon and pulp in a tank leaching system, except there's no toxic chemicals. And again, one of the advantages was they could replace these artisanal systems using mercury with something a lot less toxic. But there's precious little specific information out there on exactly how to do it. And so again, if somebody knows the actual specifics of cold gold agglomeration, I'd be very interested in that. And I'm also interested in the question about, suppose you took whatever oil is acceptable for this, the attractant, the mercury substitute, so to speak, and if you put it on an absorbent substrate, could you make the equivalent of a mercury plate, but with oil? So you have a very low toxicity material that would grab the gold right out of the slurry, and then you just scrape it off the plate or whatever. In the case of cold gold agglomeration, they usually just burn it. Once they get enough gold in it, they just burn it and then flux the ash, and there's the gold. Now that's the kind of thing that might work pretty darn well for a micro scale or a small scale operation with low permitting costs and simple and safe operation. So I'd love to find out more about that from a practical standpoint. And that's, another, what I think has a lot of promise technology there. Another thing that relates to surface chemistry is the actual tabletops, sluices, things like that. Certain materials seem to do a lot better job of stopping gold than others. One of which that I've read about in a lot of articles is rubber, just plain rubber. There was one particular one I recall where it was a particular kind of a belt and tapping and things like that, but they said that this was an actual production operation, a decent sized mine, and they were recovering gold down to 5 microns using this methodology. And one of the things is rubber seems to really be attracted to gold. So I'd also like to do some more research on that and see what can be done. This may be one of the reasons why these new ridged rubber mats, like Gold Hog mat and Keen has a mat and like this, but that may be one of the reasons why they're so good at recovering fine gold. It's not necessarily the shape, but actual adhesion of the gold to the surface. I don't know. I'd love to do some more research on that. And then we get into the final type of recovery, and that is leaching. This is where you actually dissolve the gold from the rock. Now, one of the problems with this is selectivity. You want to have some kind of a solvent, or a lixiviant is the actual technical term, that dissolves the gold without dissolving a whole lot of other stuff. You know, for example, Aqua Regia dissolves gold, but it also dissolves just about anything else. And so you're going to have a lot of crap in the solution. Now you've got to get the gold out of all this crap. So selectivity of dissolution is highly desirable. You need to have some way of getting it back out of solution. Typically this is done with ion exchange resins or with activated carbon or with precipitation. For example, they used to use powdered zinc to precipitate the gold out of a cyanide solution. There are different types of solutions. You have the old standby cyanide, inexpensive, reliable, versatile, rather slow, toxic, difficult, and very expensive to permit. If you were, for example, to have an open pit heap leach cyanide situation that you wanted to permit in the United States, you're going to have some serious deep pockets. Tens of millions of dollars, that'll get you started. Okay? Now, you can also do a tank leach if your ore is rich enough, and typically around 1/10 of an ounce to the ton in a first world country will do it, where you crush it and then you put it in a tank and agitate it and leach it, will get you a whole lot better recovery than what's known as a heap leach, where you cover an area of ground with an impermeable material, you pile rock on top of it, you sprinkle solution on it and dissolve it that way. Those are your two main methods of leaching on an industrial scale. The heap leach, the tank leach. The heap leach is very, very cheap, less than $10 a ton. And that's difficult to beat, especially when you got low-grade ores. The problem is it's not terribly efficient. If you're getting 70% recovery in a heap leach, you're doing pretty darn good. You know, you're pretty happy with that in general. A tank leach, on the other hand, you're probably going to be shooting more for the 90% plus recoveries. There comes a point where the increased recovery more than pays for the increased expense, and it just makes sense to tank leach it. When you in a micro scale operation, you're pretty much going to be reduced to tank leaching for a number of reasons. Number one, it's going to be rich. Number two, you're going to be small, so it'll be a lot easier to permit. For example, you might be able to do it in an industrial park, you know, rent a small facility there and just do it there, and make that happen legally. But there's also other lixiviants out there, thiourea, there's chlorine-based leaches. I've heard of salt and hydrochloric acid. Just a variety of different things out there. They all have their pluses and minuses. They're all more expensive than cyanide in general, although salt and hydrochloric acid would be hard to beat. They operate in a variety of pHs. Obviously, if you're using cyanide on a limestone ore, that's not going to be a problem. The limestone will help keep it in the pH range you need. But if you wanted to use an acid thiourea leach on that, good luck. That limestone is going to be just destroying your acid faster than you can add it. The cost is going to go crazy, and you're not going to be able to keep this solution stable. So it's matching the solution to the situation, matching the recovery to the solution and your solution concentrations. These are all, again, very complex questions that you quickly winnow it down to reasonable possible answers and then crunch the numbers from there. But you've got a variety of different leaching solutions with a variety of different pluses and minuses, including compatibilities with ore, costs, permitting costs, toxicities, ease of handling, etc. You have a variety of different ways of using the leaching solution, generally a tank leach, for something rich. Heap leach for big, large scale, but probably not in this country. People like you and me, don't worry about it. We don't have $1 billion to get started. And you use different ways of getting it out of solution, typically activated carbon or resins, and then those will require a stripping circuit and electroplating to get it out of them. So you've got complexity. With a gravity circuit, you can, if you can get it quickly down to a smeltable concentrate, then you just flux it, throw it in a furnace, pour it, and you're done. On a micro scale operation, and this is what I'm essentially trying to work at, it's best if you can do it with a gravity circuit. There's no chemicals involved. It's relatively simple technology. That's why you see all this stuff out there is gravity circuits. Hopefully someone will come up with flotation or cold gold agglomeration or something that can be competitive. Currently it's not, but it's right on the edge there in my opinion. But another thing is to use a gravity circuit to create a concentrate which you then could leach or smelt, depending upon how much other stuff is in it. Another thing that will often work well is you create a concentrate. Let's suppose you had a polymetallic vein, poly meaning many metals, and you got like chalcopyrite, which is a copper ore, and gold is your primary valuable minerals. So you create a chalcopyrite / gold concentrate in your mill. You then may take that concentrate and run it over a further separation to scalp out what fairly clean gold you can get, or make an easily smeltable gold concentrate. But the rest of it you might be able to ship to a processor and they'll pay you for it, because they're making money off the copper and stuff, and you might be able to do very well that way. So these are various different ways you can use to get it. But those are, in the case of a small to micro scale operation, if it's really rich, I'd say crush it, do a gravity separation to scalp out the easy gold at a minimum, and then either tank leach everything else or tank leach your concentrate, depending upon your circumstances. If your gravity concentration, in the case of gold hollow, we're getting like 90% recovery of the gold into the concentrate, which was 3 to 5% of the total. Well, that works great. Mojave 1 so far has not been nearly so cooperative, so that you might have to tank leach everything. Just crush it up and tank leach it. For that, you only need mineral exposure. You only need to grind it to the point where the valuable minerals are exposed to the leaching solutions, and that can cut your grinding costs substantially, especially if you have fine gold. If you're really trying to crush it fine, that's going to get expensive. If you can crush it less and leach it, that might save you a lot of money. So I hope this was helpful. That's kind of a quick overview of the various options and their pluses and minuses. You can research it further on the internet with your particular situation and take it from there. Various manufacturers will tend to be happy to tell you the pluses of their system and the minuses of the other person's system. I suggest asking both, and you'll get a much more balanced idea of what the heck is best for you. And I would always, you can't pre-select an extraction technique. It's all ore dependent. You need to test these things. If you got a gravity separation, crush it, pan it into a concentrate, send them off for assay. If you can't pan a good gravity concentrate and get good recoveries with it, you're probably not going to be able to do it with anything else either. And that is going to be a hell of a lot cheaper than a $5,000 or $10,000 or $20,000 machine. So for gravity separations, this is a heck of a pilot scale testing device. So hope it was useful. Hope it stimulates a lot of thought out there and helps some people out. Happy prospecting, and keep it safe out there.